On November 20th, 2025, an amateur astronomer named Diego pointed his 11-inch backyard telescope at a fuzzy patch of light moving through the constellation Camelopardalis. He wasn't expecting to make history. He was just another hobbyist chasing comets, stacking exposures in his driveway while his neighbours slept. The night air was cold, the sky a clear black canvas punctured by indifferent stars. His fingers were numb as he clicked the shutter remote, capturing frame after frame of what the catalogues called 3i Atlas, our third confirmed interstellar visitor. He was just following the routine: align, expose, track, repeat. A mundane ritual for a potentially extraordinary object. But when he processed his images 3 hours later, the glow of his monitor in the dark room illuminated something that made his breath catch. The object on his screen wasn't a blob. It was a perfect 4-pointed plasma star, a stark geometric cross emanating from a central core with a precision that seemed to violate the very chaos of space. This wasn't sublimation. This wasn't random outgassing. This was structure. It looked engineered. His hands shook as he adjusted the contrast. 4 days later, and an entire hemisphere away, another amateur named Craig aimed his 8-inch reflector at the same patch of sky. His equipment was modest, a far cry from the billion-dollar eyes of professional observatories, and when his software finished its work, Craig found himself staring not at a comet's hazy embrace, but at a rigid white core encased in a uniform symmetric blue halo. It glowed with an intense contained light, hugging the nucleus not like a natural cloud but like a force field. It looked manufactured. 2 men, working independently with mid-tier equipment, had captured something the world's space agencies had missed. NASA's publicly released images of 3i Atlas showed a featureless, slightly elongated sphere, a vague smear of light as if viewed through a grease-smeared lens. The disconnect was instant and jarring. How could backyard telescopes resolve details that spacecraft, with instruments costing more than the GDP of small nations, seemingly could not? This is where I need to pause and ask you, where are you in the world right now? What time is it where you're watching this? Let me know in the comments below. If you're as captivated by this mystery as I am, make sure to subscribe. You will not want to miss a single development as this story continues to evolve, because what comes next makes these first images look almost ordinary. The forums erupted. The astronomy community split. Some dismissed it as an artifact, over-sharpening, stacking errors, the digital ghosts that sometimes haunt processed images. Others, seasoned imagers who knew the math of pixels and algorithms, examined the raw data both men courageously released and found. The geometry was there, embedded in the unprocessed frames. It was real, the structure was real, and it made no sense. This is where our story begins. Not with a proclamation, but with a quiet, creeping realization. 2 amateur astronomers from their driveways have captured images that challenge a century of cometary science. They've seen something in 3i Atlas that shouldn't be there, a geometry that speaks not of chaos but of order, a symmetry that whispers of control. While official channels show blur, these individuals see sharp edges and defined shapes. Tonight, we are dissecting every anomaly. We're going to walk through rotation paradoxes, plasma physics, and magnetic confinement. We'll confront the uncomfortable fact that if you were designing an interstellar craft, you'd probably build something that looks exactly like this. The implications are staggering, and the journey is just beginning. This is a threshold we've never crossed before. This is part 1, the night everything changed. Symmetry in nature is a rare and precious clue. When it appears, it tells us something fundamental about the forces at work. Snowflakes form their hexagonal perfection because of the molecular architecture of water ice. Sunflowers arrange their seeds in Fibonacci spirals as a consequence of optimal packing and growth dynamics. But these symmetries emerge from simple, repetitive rules applied over and over again. They are the product of statistical inevitability, not of a single, violent event. A comet is a violent event. It is a tumbling, fractured chunk of primordial ice and rock, a dirty snowball, or more accurately a snowy dirt ball. Its surface is a nightmare landscape of craters, fissures, and jagged ridges. As sunlight falls on one face, ices don't melt. They sublimate, turning directly from solid to gas in explosive jets that erupt from specific weak points. These jets are directional, uneven, and transient. As the nucleus rotates, new facets bake in the sun, activating new jets while others sputter and die. The resulting coma, the cloud of gas and dust, should look like someone threw a handful of glitter into a hurricane. It should be asymmetric, chaotic, messy. It should be by definition disordered. When Diego and Craig processed their images of 3i Atlas through symmetry analysis software, they expected a score reflecting that inherent chaos. For a typical comet, bilateral symmetry, the degree to which the left and right halves mirror each other, falls between 30% and 50%. The software compared pixels, measuring the mirror match. The number that came back was 94%. 94%. That number doesn't just suggest organization, it screams it. It is a statistical impossibility for a natural comet nucleus behaving in a natural way. To understand why this is so profoundly wrong, you have to internalize the reality of a comet's life. It is a system falling apart in real time. It is bleeding mass into the vacuum with every second it spends near the sun. For it to maintain a 94% bilateral symmetry, it would need to regulate its outgassing with the precision of a Swiss watch. It would need to compensate for changes in solar heating, for the irregular erosion of its surface, for its own chaotic tumble. That requires feedback. It requires response. It requires a system that monitors its own state and adjusts. We have no natural precedent for that in cometary science. We have precedent in engineering, in satellites with attitude control systems, in probes that fire thrusters to maintain orientation. The immediate default explanation from the skeptical camp was rotational averaging. The idea is simple: spin anything fast enough, and its asymmetries blur into a uniform glow. A spinning ceiling fan's blades vanish into a solid disk. Perhaps, the argument went, Atlas is spinning so rapidly that its individual jets are smeared into this apparent symmetry. The math is plausible, but the consequences are catastrophic. Comets that spin rapidly show telltale signs. They develop equatorial bulges. They fling material away, forming secondary clouds and debris streams. Their light curves pulse with a regular rhythm as bright and dark sides rotate into view. 3i Atlas shows none of this. Its brightness is stable, not pulsing. Its shape is rigid, not deforming. Its coma is compact, not spraying debris. To achieve this level of symmetry through rotation alone, Atlas would need a spin period measured in minutes, perhaps even seconds. At that speed, centrifugal forces would overcome the pitifully weak gravity holding a rubble pile comet together. It would tear itself apart in hours, scattering its guts across millions of kilometers. This is the rotation paradox in its raw form. To create the symmetry, Atlas must spin impossibly fast. But to survive that spin without disintegrating, it must be impossibly strong. Comets are not strong. They are fragile agglomerations of ice and dust, held together by the faintest whisper of self-gravity and material friction. They are the very definition of weak. And yet, here is Atlas, symmetric, intact, and defying the centrifugal guillotine. Throughout history, amateurs have occasionally reported geometric patterns in comets, and most have been debunked. Lens flares, diffraction spikes from telescope supports, compression artifacts, overprocessing, these can all create false structure, but those explanations dissolve under scrutiny here. Diego used a Schmidt-Cassegrain telescope, and design prone to specific optical artifacts. Craig used a Newtonian reflector, with a completely different optical signature. Their cameras had different sensors, different pixel sizes. They were on different continents, under different atmospheres, on different nights. Yet the symmetry, the 4-point star, the blue halo, these features appeared in both data sets, consistent in position, morphology, and even color distribution. This is the hallmark of a real feature, not an artifact. Something intrinsic to 3i Atlas is generating organized light. Natural. Processes can sometimes mimic order. Planetary nebulae, the beautiful graves of dying stars, often show breathtaking symmetry, likely shaped by binary companions or magnetic fields. Saturn's hexagonal north polar storm is a stable atmospheric phenomenon, but these are steady-state systems, sustained by continuous massive energy input. A comet is a transient, decaying system. For it to maintain symmetry is like expecting the smoke from a snuffed candle to hold the shape of the flame. It goes against the gradient of entropy. It resists the pull toward disorder. The possibility of a single symmetric outburst was floated, a perfectly centered explosion of subsurface gas. But outbursts are, by nature, chaotic releases of pent-up stress. They cannot be geometrically perfect, and more damningly, the symmetry in Atlas wasn't a flash. It persisted. From November 20th through at least the 28th, over a dozen independent observers captured it. This was a sustained configuration, maintained as the comet moved, as the solar angle changed, as the violence of sublimation continued unabated. Sustained symmetry demands sustained organization. So we are left with the image, and the chilling question it forces us to whisper. Is 3i Atlas actively maintaining its shape? Does it possess some form of regulation? The implications of even asking that question ripple through everything we think we know, and as we stare at that 94% symmetry score, a number that belongs in an engineering textbook, not a comet observation log, we realize the anomaly is not softening, it is hardening. And the structure was just the opening act. The tail is the soul of a comet. It is its defining feature, its most reliable behavior, governed by straightforward, elegant physics. The solar wind, a 1,000,000-mile-per-hour stream of charged particles blowing from the sun, pushes against the comet's released gas and dust. This creates a tail that always points away from the sun, like a cosmic windsock. It can stretch for millions of kilometers, a glowing streamer against the black. It is predictable. It is consistent. It is one of the few things in astronomy we thought we understood completely. So when 3i Atlas's tail began to misbehave, it wasn't just an anomaly, it was a violation. In Diego's images from November 20th, alongside the 4-point star, there was something even more perplexing. The tail wasn't streaming away. It appeared flattened, wrapped around the nucleus in a ring-like structure, a torus. It was as if the solar wind had been bent at right angles, compelled to flow in a circle. 4 days later, Craig's images delivered the next shock. The tail had almost completely vanished. What remained was that tight blue halo clinging to the coma. The long, luminous streamer was gone, collapsed inward as if the object had swallowed its own exhaust. To understand how profoundly bizarre this is, imagine standing in a river and releasing a cloud of dye. The current carries it downstream, stretching it into a long, thin plume. The dye does not curl back and form a perfect ring around your hand. It does not reverse direction and cluster at the source. For that to happen, you would need a force actively pushing against the current, a force equal to or greater than the river's flow. In space, the solar wind is that river. For a comet's tail to flatten into a torus, something must be redirecting the outflowing material, bending it perpendicular to the radial push of the sun. Magnetic fields can do this. Rapidly rotating, self-confined plasma can do this, but both require energy and organization far beyond what a passive chunk of ice should possess. Ring-shaped structures in comas have been glimpsed before, but they are fleeting, transient spirals that last hours before being shredded by solar wind. Comet Hale-Bopp in 1997 showed some, but Atlas's toroidal structure persisted. For at least 4 days, and likely longer, it held its shape. Stability in the dynamic, violent environment of a coma requires continuous input. It requires maintenance. The solar wind's pressure alone should have ripped that ring apart within hours, yet there it was, frame after frame, night after night, defying the very force that defines what a comet is. Craig's November 24th. Images introduced the next level of strangeness. The ring had tightened, compressing inward until it was barely distinguishable from the coma itself. The tail was not just bent, it was gone. What remained looked less like a comet and more like a miniature magnetosphere, the kind of protective magnetic bubble that surrounds planets like Earth and Jupiter. Comets do not have magnetospheres. They are too small, too cold, too geologically dead to generate the internal dynamos that create planetary magnetic fields. Yet the visual resemblance was uncanny. It was as if Atlas had wrapped itself in a cocoon, suppressing the very process that makes comets visible. The brightness data compounded the mystery. Comets brighten as they approach the sun in a smooth, predictable curve. More heat, more sublimation, a larger coma. 3i Atlas did not follow that curve. On November 22nd, its brightness spiked suddenly, an increase not correlated with any change in distance from the sun. It dimmed slightly, then spiked again on November 26th. These fluctuations happened over days, far too fast to be caused by changing solar distance, and they occurred while the tail was collapsing, which should have made the comet dimmer overall, not brighter. It was as if the object was concentrating its energy, pulling its diffuse glow inward, intensifying the core while suppressing the tail. That is not how passive objects behave. That is how active systems behave when they reallocate resources. Multiple observers across different continents, in Australia, Spain, Chile, reported the same toroidal morphology within a 12-hour window. When their images were placed side by side on the forums, the consistency was eerie. Same tilt angle, same brightness distribution, same blue hue. This was not an artifact. This was a real, physical structure, and it was behaving in ways that no natural comet coma should. The inverted coma hypothesis emerged from this data. Instead of material being pushed away, it appeared to be trapped, circulating around the nucleus in a stable configuration. For this to happen, you need a confining force. In laboratory plasma physics, we use magnetic fields to confine charged particles into toroidal shapes. This is the basis of tokamak fusion reactors. In space, planetary magnetospheres trap solar wind particles into radiation belts. But those systems have active magnetic fields. Comets do not, unless, of course, this one does. The speculation grew darker, whispered in private messages, dismissed publicly, but gnawing privately. If 3i Atlas is suppressing its tail, why? Comets have been shedding tails for billions of years. It's fundamental to their nature. Suppressing a tail is like suppressing evaporation from boiling water. You would need to actively counteract a natural process. The only conceivable reason to do that, the only logical motivation, is stealth. A large, diffuse tail is a beacon, visible across vast distances. A compact, dim object with a tight halo is harder to detect, harder to track, easier to overlook. That thought, that Atlas might be trying to reduce its visibility, infected the analysis. It sounded like paranoia, but it emerged coldly from the observable data. The vanishing tail and inverted coma opened a door to ideas that straddle the line between astrophysics and science fiction. They forced a confrontation with plasma dynamics and magnetic confinement, and with the uncomfortable parallels between what we observe and what we would expect from a system that is not just tumbling, but functioning. The disconnect between the official imagery and the amateur captures wasn't just a discrepancy, it was a chasm. It felt almost offensive in its magnitude. NASA's publicly released images, captured by spacecraft and ground-based observatories with budgets measured in billions, showed a fuzzy, elongated blob. No structure, no geometry, no blue halo, just a smear of light against the black, the kind of image that confirms presence but obscures nature. Meanwhile, hobbyists using gear bought on credit cards were resolving 4-point plasma stars, symmetric toroidal rings, and rigid halos. The cognitive dissonance was too large to ignore. Either the amateurs were collectively hallucinating details that weren't there, or the professional institutions were systematically missing details that were. And with each passing day, the evidence leaned more heavily toward the latter. There are legitimate mundane reasons for this disconnect. Spacecraft imaging operates under brutal constraints that a backyard astronomer never faces. When you're on a spacecraft moving at tens of thousands of kilometers per hour relative to your target, that target is a moving dot. Long exposures, necessary to gather light from faint objects, result in motion blur. To compensate, missions use short exposures and stack frames, the same technique amateurs use, but then they hit the wall of bandwidth. Transmitting high-resolution images across hundreds of millions of kilometers is slow and power-hungry. So images are compressed, downsampled, and binned. Sensor binning combines adjacent pixels into superpixels, boosting sensitivity at the fatal cost of resolution. A 2x2 bin turns 4 pixels into 1, quadrupling the signal but halving the resolution in each dimension. For a faint comet at the edge of detection, binning is often necessary to see anything at all. It's a devil's bargain. You see the object, but you lose the fine structure that might tell you what it truly is. Furthermore, professional data processing is inherently conservative. A standard step is anti-aliasing smoothing, which rounds off jagged pixel edges to prevent the publication of false features. This practice is born from decades of embarrassing retractions where structures turned out to be instrumental artifacts. The institutional mantra is caution. Better to show a smooth, slightly blurry image than to mislead with sharp details that aren't real. But what if the details are real? What if the sharp edges, the geometric patterns, the toroidal structures are genuine, and the smoothing algorithms are erasing the very information we need? That is the nightmare scenario quietly unfolding around 3i Atlas. Institutional caution could be obscuring the truth. Into this gap, conspiracy theories naturally flowed. Online forums buzzed with accusations that NASA and other agencies were intentionally suppressing detail, that a global agreement was in place to downplay the strangeness of Atlas to prevent public panic. The logic was seductive. If an interstellar object shows signs of artificiality, revealing that could trigger societal chaos, religious upheaval, economic collapse, better to show a blurry comet, let the public assume it's natural, and handle the implications behind closed doors. It's a narrative that feeds on distrust and a hunger for hidden knowledge. But it is almost certainly wrong. Governments are terrible at keeping secrets of this scale. Too many people are involved, thousands of astronomers across hundreds of institutions in dozens of countries. If there were explicit orders to hide structural details, a leak would be inevitable. The more boring explanation is far more likely. Space agencies prioritize different science. They are focused on spectroscopy, what the object is made of, and on trajectory, where it's going. Morphology, the shape of the coma, is often secondary. They don't allocate precious computational resources to high-resolution imaging because for most of their goals, it isn't necessary. They leave that to the amateurs. Yet, even accepting this mundane explanation, a troubling question remains. Why are multiple independent amateurs, using different equipment and processing pipelines, all capturing the same geometric structures? If these were artifacts, you'd expect variation, different patterns from different telescopes. Instead, you get consistency. The 4-point star appears in images processed with PixInsight, Deep Sky Stacker, and custom Python scripts. The blue halo shows up in data from CMOS cameras, CCDs, and modified DSLRs. The torus is visible from both hemispheres. This level of consistency is the hallmark of a real feature, not a glitch. History supports the idea that amateurs can see what professionals miss. Amateur Alan Hale co-discovered the Great Comet Hale-Bopp. An amateur in Australia captured an impact on Jupiter that professional observatories missed. Amateurs discovered a massive storm on Saturn before any major telescope noticed. Amateurs have time, flexibility, and obsessive attention to detail that large surveys often lack. They can watch one patch of sky all night. They can process data with a personal investment no contracted analyst might have. There's also the wavelength question. NASA's spacecraft often observe in infrared or ultraviolet, bands crucial for understanding composition and temperature. Amateurs work almost exclusively in visible light, the light our eyes evolved to see. It is possible Atlas looks fundamentally different in different wavelengths. The blue halo, prominent in visible light from ionized molecules, might be diffuse or absent in infrared. This could explain the discrepancy without conspiracy. Different tools see different things, but even granting that, the core mystery persists. Visible light is arguably the most important band for understanding morphology. It's what we see. If 3i Atlas exhibits organized geometric structure in visible light, that is significant regardless of what it looks like elsewhere. Shape matters. Structure matters. And the structure amateurs are capturing suggests an organization that simply should not exist in a natural comet. So we are left with an uncomfortable possibility. Maybe NASA's blur isn't a deliberate cover-up. Maybe it's just the result of different priorities and conservative processing. But the result is the same. The public sees smooth, featureless images from official sources, while independent observers resolve a geometry that challenges our understanding of reality. And in that gap between institutional caution and amateur discovery, the truth about 3i Atlas lurks, unresolved and growing more urgent by the day. Powering up. It's a dangerous phrase in astronomy. It implies intention, agency, decision-making, terms we reserve for living things or engineered systems. Comets don't power up. They heat up. They brighten passively as solar radiation vaporizes their surfaces. The process is thermodynamic, governed by physics, not choice. Yet, watching the brightness curve of 3i Atlas through November 2025, it's hard to find another phrase that fits. The object wasn't just getting brighter, it was behaving like a system coming online. Coherence was increasing, structure was tightening, geometry was sharpening. It was as if something inside was waking up after a long cold sleep through the interstellar void. The brightness spikes told a story that violated standard cometry models. On November 22nd, Atlas brightened by 0.7 magnitudes in just 12 hours, a surge not correlated with its approach to the Sun. It was still over 2 astronomical units out, where solar heating should have been relatively constant day to day. Comets at that distance brighten gradually, smoothly. Atlas spiked, then it settled. Then, on November 26th, it spiked again by nearly a full magnitude over 18 hours. These weren't outbursts. Outbursts show rapid brightening followed by an exponential decay as ejected material disperses. These were plateaus, sustained increases in brightness that lasted for days, as if energy was being channeled more efficiently, concentrated into the core rather than dissipated. Typical comets get messier as they approach the Sun. Increased heating vaporizes more ice, expands the coma, activates new jets. The result is a larger, more chaotic, more diffuse cloud. 3I Atlas did the opposite. As it brightened, its coma tightened. The halo contracted. The toroidal structure became more defined, not less. It was as if the object was consolidating, pulling itself together, organizing its energy output into coherent patterns rather than allowing it to scatter randomly. That is not passive thermodynamic behavior. That is active regulation, the kind of thing you see in a system with feedback loops and control mechanisms. A natural explanation called thermal annealing was proposed. The idea is that as a comet heats, softer ices sublimate first, leaving behind a smoother, harder, more refractory crust. A smoother surface could, in theory, reflect light more uniformly, creating an appearance of symmetry. It's an elegant hypothesis, and it is utterly insufficient. Thermal annealing is a surface process. It cannot produce 94% bilateral symmetry in a 3-dimensional cloud of gas and dust. It cannot create a 4-point plasma star. It cannot collapse a 1,000,000-kilometer tail into a toroidal ring. You cannot anneal plasma. You cannot smooth a magnetic configuration. The organization we are observing is happening in the coma, in the material after it has left the surface. It requires forces acting upon that material. History provides a stark contrast. Comet Linear, C99S4, fragmented spectacularly in 2000 as it approached the Sun. Comet Neowise, C2920F3, brightened predictably, its coma expanding and diffusing exactly as expected. Comet Shoemaker-Levy 9 broke into over 20 fragments before plunging into Jupiter. The pattern is clear and consistent. Comets under stress fall apart. They do not organize, they do not tighten, they do not show increasing symmetry. Yet here is 3I Atlas subjected to solar heating, tidal forces, and radiation pressure, and instead of fragmenting or diffusing, it is becoming more structured. The concept of coherence increase appears in plasma physics. Certain plasma configurations become more stable, more organized, as energy input crosses a critical threshold. In a tokamak, below a certain temperature, the plasma is turbulent and lossy. Above it, magnetic fields lock it into a stable, organized shape, sustaining confinement. The parallel to Atlas is uncomfortable but unavoidable. If its coma is partially ionized, and if there is a magnetic field present, then increased solar heating could ionize more material, strengthening the magnetic coupling. This could create a positive feedback loop. More energy leads to better organization. It's speculative, but it fits the data better than any passive model. The tightening halo, observed over days, suggests energy concentration. In engineering terms, you'd call this collimation, the process of focusing diffuse energy into a directed beam or compact volume. Flashlights collimate light with reflectors. Lasers do it with resonant cavities. Magnetic nozzles collimate plasma using shaped magnetic fields. If 3I Atlas is collimating its coma, whether deliberately or through a natural but unknown process, it would appear exactly as observed, a shrinking, brightening core with a tightly confined halo. The question is whether such collimation can occur naturally in a comet. Based on every comet we've ever studied in detail, the answer is no, which leaves us facing the possibility that 3I Atlas isn't behaving naturally. This is where the conversation becomes dangerous. Suggesting a comet might be engineered invites immediate ridicule from the scientific establishment, and immediate uncritical credulity from the fringe. It's a no-win proposition. But ignoring data because it points toward uncomfortable conclusions is intellectually dishonest. Science is supposed to follow evidence, not comfort. And the evidence piling up night after night suggests Atlas is doing things comets do not do. It maintains symmetry. It confines its coma. It spikes in brightness independently of solar heating. It collapses its tail. Any one of these, in isolation, could be dismissed as a rare anomaly. But observing them all together, in the same object over a sustained period, strains the boundaries of coincidence past the breaking point. The final, simple, terrifying observation is this. As 3I Atlas moves deeper into the inner solar system, its behaviour isn't decaying toward normality. It's escalating. The geometry isn't softening, it's sharpening. The glow isn't dimming, it's intensifying. Whatever is happening to this object, it is accelerating, building towards some threshold or transition we cannot yet predict. If Atlas were just an unusually symmetric comet, we'd expect its strangeness to fade as better data revealed prosaic explanations. Instead, every new observation deepens the mystery. And that pattern, that escalation of anomaly, is exactly what you would expect from a system that is not broken, but activating. Coming online, preparing for whatever comes next. Rotation might explain everything, or it might explain nothing. It is the go-to hypothesis for researchers attempting to reconcile Atlas's symmetry with natural phenomena. The argument is appealingly simple. If 3I Atlas is spinning rapidly enough, the coma averages out into apparent uniformity. Individual jets and asymmetries blur together, like the spokes of a spinning wheel, creating the illusion of a symmetric organized structure. It invokes only known physics. It requires no exotic materials. It is the safe, conservative explanation. The problem is that when you run the numbers, the hypothesis collapses under the weight of its own implications. To achieve the observed 94% symmetry, Atlas would need to spin so fast that it should have torn itself apart days ago. Rotational breakup is a well-understood limit. Every object has a critical rotation rate beyond which centrifugal forces exceed the self-gravity holding it together. For a rubble pile comet, a loosely bound collection of ice and rock chunks, that critical rate is very low. Most comets rotate with periods measured in hours or days. The fastest rotating comet on record, P2013 R3, had a period of about 3.5 hours, and it was actively fragmenting, shedding mass from its equator. For 3I Atlas to smooth its coma through rotation alone, it would likely need a period under an hour, possibly under 30 minutes. At that speed, the centrifugal acceleration at its equator would be dozens of times stronger than its minuscule surface gravity. A loosely bound comet would not just shed material, it would explode, fragments flying off tangentially like water from a spinning wet basketball. The mathematics is straightforward and brutal, yet 3I Atlas shows none of the signatures of a fragmenting body. Its nucleus appears intact. Its coma, though toroidal, shows no spray patterns, no secondary nuclei, no debris clouds. This is the heart of the rotation paradox. To create the symmetry, it must spin impossibly fast. But to survive that spin without disintegrating, it must be impossibly strong. Comets are not strong. They are the antithesis of strong. They are fragile aggregates, barely holding themselves together. Angular momentum considerations deepen the paradox. Interstellar objects are typically expected to have slow rotation. The gravitational interactions that eject them from their home star systems tend to dampen spin. For Atlas to arrive spinning rapidly, something unusual must have happened. Either a spin-up mechanism we don't understand, or it was launched with high rotation and has maintained it across light years of travel, which itself is a monumental engineering challenge. The toroidal coma adds another layer of complexity. If you model the coma as a rotating ring of gas and dust, its stability depends on a precise balance between rotational inertia, trying to fling material outward, and dispersive forces like solar wind, trying to push it radially away. For this balance to hold stably for days, it would require either incredible luck or active stabilization. In fluid dynamics, such structures can be metastable, persisting for a while before turbulence breaks them apart. But cometary comas are not simple fluids. They're a messy mix of neutral gas, dust, and collisionless plasma, subject to electromagnetic forces, radiation pressure, and gravity simultaneously. Stabilizing such a system through rotation alone is like balancing a pencil on its point while riding a unicycle on a tightrope. Theoretically possible, implausible in practice. Some researchers have proposed magnetic stabilization as a solution. If 3I Atlas has an intrinsic magnetic field, it could confine ionized gas into organized structures without requiring extreme rotation. Magnetic fields can trap, guide, and shape plasma in ways gravity never could. Earth's magnetosphere does this. Jupiter's magnetic field creates vast plasma tori around its moons. If Atlas has even a modest magnetic field, it could organize its coma into the observed toroidal geometry. The catch, of course, is that comets do not generate magnetic fields. They are geologically dead. No molten cores, no dynamos, no internal heat source to sustain a field over geological time. Unless the field isn't generated internally, but is induced by external currents, or is a remnant field frozen into an unusually metal-rich nucleus. The parallel to human technology is, once again, unnerving. Magnetic confinement in laboratories, in tokamaks and stellarators, relies on external coils to generate carefully shaped magnetic fields that hold million-degree plasma in a stable, toroidal configuration. The plasma never touches the walls. The fields push it back, confining it. If you squint, the resemblance to Atlas's coma is uncanny. A glowing torus of ionized gas confined by magnetic fields, rotating to maintain stability. The difference is that tokamaks are engineered devices with megawatts of power and precisely wound superconducting coils. Atlas is supposed to be a natural object, yet the morphology matches, the stability matches, the symmetry matches. It is as if someone built a tokamak and threw it into interstellar space. This paradox, the spin rates that should tear it apart and the cohesion that somehow holds it together, sits at the center of the Atlas mystery. Every conventional explanation requires violating at least one fundamental physical constraint. Rapid rotation explains symmetry, but demands impossible strength. Magnetic confinement explains stability, but requires fields comets shouldn't have. Thermal processes explain brightening, but cannot account for organization. We are left juggling impossibilities, trying to find a combination that violates physics the least, and increasingly, the least violated model is one that invokes active systems, feedback mechanisms, and energy management, capabilities far beyond what a passive ice ball can achieve. The rotation paradox isn't just a puzzle to be solved, it is a signpost, pointing stubbornly toward explanations we would rather not consider. Because if Atlas isn't spinning impossibly fast, and if it isn't impossibly strong, then the symmetry and stability must come from something else. Something that monitors, adjusts, and maintains. Something that behaves less like geology and more like engineering. The blue glow haunts every image. It is not the warm yellow-white of reflected sunlight, nor the green tint of diatomic carbon common in comets. It is a distinct electric blue, the colour of ionized gas energized by processes more intense than simple solar heating. Spectroscopic analysis points toward ionized carbon monoxide, the CO+, a common component in comet tails, formed when ultraviolet light strips electrons from CO molecules. That part is normal. What isn't normal is the intensity, the uniformity, and the spatial distribution. The glow hugs the nucleus too tightly. It is too even. It persists too consistently. It looks, in a word that makes physicists uneasy, designed. And that resemblance to engineered plasma systems is not superficial. Plasma sheets form when ionized gas interacts with a boundary. Around a spacecraft in Earth orbit, the electrically conductive hull interacts with the ionosphere, creating a thin layer where electric fields shape particle motion. These sheaths are microscopic, but they affect everything from communications to drag. Scale that concept up. Imagine an object moving at interstellar velocities, ploughing through the thin soup of ionized hydrogen and microdust. The interaction creates a bow shock, a compressed region ahead of the object, and potentially a trailing plasma sheath. If the object has any electrical conductivity or carries a charge, this sheath could organize into observable structures. This is natural, expected. But the geometry we see in Atlas goes far beyond a simple bow shock. It shows toroidal symmetry, tight confinement, and stability over days. That requires more than passive interaction. Magnetic tori, donut-shaped plasma structures confined by magnetic fields, are the workhorses of fusion research. A tokamak generates a toroidal magnetic field with external coils, then induces a current in the plasma itself. The combined fields twist into helical paths that trap the hot plasma away from the reactor walls. Visually, from certain angles, these laboratory plasmas look eerily similar to the blue halo surrounding 3i Atlas. Same shape, same glow, same tight confinement. The solar wind shapes cometary comas, but usually into elongated teardrops, not perfect tori. Magnetic field lines in the solar wind can drape around a comet, creating current sheets. But these are typically asymmetric, distorted by the comet's motion and uneven outgassing. To create a symmetric torus, you need either an axially symmetric outgassing pattern, improbable given an irregular nucleus, or a confining field so strong it overwhelms local asymmetries. Planetary magnetospheres achieve this through powerful intrinsic fields. Io, Jupiter's volcanic moon, is embedded in Jupiter's magnetic field, which traps ions from Io's volcanoes into a massive plasma torus that orbits the planet. The Io plasma torus is one of the most prominent toroidal structures in our solar system, and it exists because of external magnetic confinement. If 3i Atlas were embedded in a strong local magnetic field, either intrinsic or induced, it could theoretically create a miniature version of this. But where would such a field come from? The concept of controlled ionization offers a speculative but fascinating mechanism. In spacecraft engineering, plasma contactors deliberately ionize gas to control electrical potential, preventing damaging charge buildup. Electric propulsion systems like Hall thrusters ionize propellant and accelerate it using electric and magnetic fields to generate thrust. If a spacecraft were traveling at high speed through the interstellar medium, it might intentionally create a plasma bubble around itself using controlled ionization and magnetic shaping. This bubble would deflect microdust and charged particles, a form of active shielding, and it would glow, emitting light from recombination and excitation processes. From a distance, it would appear as a symmetric halo around the craft. The resemblance to Atlas's blue glow is uncomfortable because it suggests functionality. The glow isn't waste, it's operational. It is a byproduct of a working system. Solar magnetic field lines interacting with a charged or magnetic object can create complex structures. If Atlas has any magnetic moment, the Sun's magnetic field could interact with it, potentially organizing the coma plasma into shapes more stable than random outgassing would produce. This is a natural process in principle, but the level of organization in Atlas's coma exceeds anything we've observed elsewhere, suggesting either an unusually strong interaction or something more deliberate. Speculating about protective bubbles ventures into science fiction, but it is grounded in real physics. High-speed travel through even the tenuous interstellar medium is hazardous. At 10% the speed of light, a collision with a grain of dust releases energy equivalent to a hand grenade. Over centuries of travel, countless such impacts would erode any surface. One proposed solution in theoretical studies of interstellar travel is to generate a magnetic or plasma bubble ahead of the spacecraft, deflecting particles before they impact the hull. Such a bubble would need to be just conductive enough to divert charged particles and ionize incoming neutrals so they too can be deflected. It would glow from the energy dissipated. It would be symmetric if the generating field was symmetric, and it would be tight to the craft to minimize energy expenditure, exactly as we observe in Atlas. Natural plasma structures provide important context but also highlight the difference. Earth's magnetosphere is a protective bubble. Auroras are visible plasma dynamics. Solar coronal loops demonstrate magnetic confinement on massive scales. Comets themselves generate ion tails that glow blue. All are natural. None are toroidal, symmetric, and tightly confined in the way Atlas's coma appears. Nature can create plasma structures, but the specific, stable, geometric configuration we observe is rare, requiring a confluence of conditions that do not typically coexist in a comet. The smoothness and symmetry stand out not as impossible, but as so improbable that they demand we consider alternatives. The distinction between natural and engineered plasma structures often boils down to stability and symmetry. Natural structures are messy, dynamic, shaped by turbulent interactions and chaotic initial conditions. Engineered structures are smooth, stable, designed to minimize energy loss and maximize function. When you compare images of tokamak plasmas with images of Atlas's halo, the resemblance isn't perfect, but it is closer than the resemblance between Atlas and any natural comet. That doesn't prove anything. Resemblance is not evidence. but it is suggestive, and when combined with the rotation paradox, the vanishing tail, and the anomalous brightness spikes, the cumulative weight of observation pushes toward a conclusion that feels both inevitable and absurd. Either we are witnessing the most anomalous natural comet in recorded history, or we are witnessing something that was engineered to look like a comet while performing functions comets do not perform. The glow, the halo, the toroidal symmetry. They might not just be pretty. They might be functional, and that possibility, however uncomfortable, refuses to go away. Let's set boundaries immediately. This is not about declaring 3i Atlas an alien spacecraft. This is about exploring what an engineered interstellar object would need to do to survive the journey between stars, and then noticing, uncomfortably, that Atlas exhibits several behaviours consistent with those engineering requirements. We are not claiming proof. We are asking what engineering logic would demand, and observing that the anomalies we've documented align with that logic more closely than they align with natural cometary behaviour. This is speculative astrophysics meeting engineering analysis. And it is crucial to state clearly, we are observers asking uncomfortable questions, not scientists making claims. An interstellar craft travelling for thousands or millions of years faces survival challenges that dwarf anything in our solar system. Cosmic dust, though sparse, becomes a sandblaster at relativistic speeds. A grain of sand impacting at 10% light speed carries kinetic energy equivalent to a car crash. Over millennia, countless such impacts would ablate any exposed surface to nothing unless protected. Whipple shields, multi-layer bumpers used on the ISS, work by vaporizing particles in outer layers, but they are passive, they degrade. For journeys lasting eons, active protection might be necessary. Plasma shields represent one speculative approach. By generating a magnetic field and ionizing gas ahead of the craft, incoming particles could be deflected or slowed. The concept appears in theoretical Bussard ramjet designs, where a magnetic scoop collects interstellar hydrogen for fuel. The same field that collects fuel also deflects dangerous particles, creating a protective cocoon. Such a shield would glow, it would be roughly symmetric, and it would be essential for long-duration travel. Radiation is another existential threat. Galactic cosmic rays would destroy electronics and degrade materials over centuries. Thick shielding adds immense mass. Magnetic deflection, creating a protective bubble, is a more elegant solution. That bubble would, again, produce a glowing plasma sheath, a symmetric halo. The parallels to Atlas's blue glow become harder to dismiss. Magnetic storms in the interstellar medium could induce damaging currents in a conducting craft. Active magnetic management, using onboard field generators to counteract or exploit external fields, might be necessary for navigation and protection. Such systems would dynamically adjust, potentially producing observable changes in plasma configuration. If Atlas is actively managing a magnetic bubble, we might expect brightness fluctuations, geometry changes, or toroidal reshaping as it responds to the solar environment. That is exactly what we observe. Rotational stabilization is fundamental to spacecraft design. Spin provides passive stability without constant thruster use. For an interstellar craft, spin also serves to average out exposure, distributing heat, radiation, and particle impacts evenly across the surface to prevent localized degradation. This rotational averaging naturally produces symmetric external signatures. A rotating craft with a plasma bubble would appear, from a distance, as a symmetric glowing object, exactly as Atlas appears. Energy blooming is a speculative but plausible concept. If a craft is powered by systems that degrade, it might plan its trajectory to pass near stars, using stellar radiation to recharge. As it approaches, dormant systems could activate, brightening its electromagnetic signature. Atlas's brightness spikes, not tied to perihelion, could fit this pattern if the object is powering up systems in response to increasing solar energy availability. It explains the timing better than sublimation models do. We observe coherence, the maintenance of organized structure. We observe symmetry, geometric precision. We observe brightness modulation, changes not predicted by passive heating. These are all features you would expect from a controlled system responding to its environment. They are not proof of engineering, but they are suggestive of it. And when you place them alongside the historical mystery of Oumuamua, with its own unexplained non-gravitational acceleration and complete lack of visible outgassing, a pattern emerges. Two interstellar objects, both exhibiting behaviors that strain natural explanations to the limit. Oumuamua accelerated without visible jets. Atlas organizes its coma without apparent cause. Either we are incredibly unlucky, encountering the two strangest natural objects in recorded history within 8 years of each other, or we're encountering something that was never natural to begin with. The intelligence hypothesis does not require biology or consciousness. It requires only engineering, the application of physical principles to achieve specific outcomes. A probe launched millions of years ago by a civilization long extinct could still function, executing pre-programmed instructions, maintaining its systems, navigating towards stars as waypoints. It wouldn't think, it wouldn't communicate, it would just operate, following the logic burned into its circuits. And to us, observing from a distance, it would look strange, organized, purposeful, not because it's alive, but because it's functional. The question isn't whether 3i Atlas is intelligent. The question is whether it is engineered. And increasingly, the anomaly suggests that if it is just a comet, it's the unluckiest comet in the universe, exhibiting every single trait that would make us suspect artificiality, without quite crossing the threshold into undeniable proof. Or maybe it's not unlucky. Maybe it's exactly what it looks like. The systematic blur in institutional imaging of fast-moving objects is a fact of physics and engineering, not necessarily malice. When a spacecraft images a comet from a distance while both are moving, short exposures are a must to prevent smearing. Short exposures mean low signal. The solution is frame averaging. Take many short frames, align them, and stack them. This works if the alignment is perfect, but estimating the motion of a faint distant dot is hard. Small errors accumulate, blurring fine detail. The algorithms used by missions prioritize robustness. They would rather produce a smooth, slightly fuzzy image than a sharp one riddled with alignment artifacts. The result is a systematic, inevitable loss of detail. Sensor binning compounds this. It combines pixels before readout to reduce noise and data volume. A 2x2 bin turns 4 pixels into 1. You gain sensitivity but throw away 3/4 of your spatial information. For a faint target, binning is often mandatory. You cannot see the object without it, but once binned, that detail is gone forever. You cannot recover what was never recorded. For most scientific goals, measuring brightness, color, composition, this is an acceptable trade. For understanding morphology, it's a disaster. Anti-aliasing smoothing is another standard conservative step. When a circular object is digitized onto a square pixel grid, its edges become jagged. Smoothing algorithms interpolate between pixels to create visually clean, rounded edges. This prevents the publication of false, pixelated structures. But it is a double-edged sword. If an object genuinely has sharp, geometric edges, like a 4-pointed star or a torus with a defined inner hole, anti-aliasing will soften them, making engineered geometry look more like a natural, fuzzy coma. Amateurs, processing their own data with less institutional caution, might skip or minimize this step, preserving the sharp details that professional pipelines erase. This explains the discrepancy without conspiracy. Different philosophies, different results. The conspiracy angle, however, is seductive. It argues that space agencies are intentionally hiding detail to prevent public alarm. Proponents point to historical cover-ups and the secrecy surrounding aerospace projects. If an interstellar object showed signs of artificiality, revealing it could destabilize society. Better, from a governmental perspective, to quietly study it and release sanitized imagery. It's a narrative that fits our cynicism. The counter-arguments are practical. Secrets of this magnitude don't stay secret. Too many people across too many nations and institutions are involved. Whistleblowing is inevitable. Global coordination with perfect fidelity is a fantasy. The mundane explanation that agencies process data conservatively for good scientific reasons is far more plausible. Bandwidth constraints are severe and real. Spacecraft transmit data at agonizingly slow rates across interplanetary distances. High-resolution images are huge. Transmitting them takes time and power that must be budgeted against other priorities, so data is compressed, downsampled, and prioritized. Only the most critical data gets full resolution. Morphology often isn't top of the list. This perfectly explains why amateurs with no bandwidth limits and unlimited local processing power, can produce sharper images. The discrepancy is expected, not suspicious. Raw data complexity is another barrier. Spacecraft images arrive as raw, uncalibrated sensor data, full of noise, cosmic ray hits, and optical distortions. Turning this into a publishable image requires expertise and choices about color balance, contrast, and artifact removal. Different choices yield different images, all technically valid but visually distinct. NASA releases images balanced for public consumption and scientific prudence. Amateurs might push contrast and sharpness to the limit, revealing subtle details at the risk of also creating noise. The fact that multiple amateurs see the same details suggests those details are real, but institutional caution prevents official confirmation until verification is exhaustive. This caution is a learned response. Astronomy has a history of false discoveries from processing artifacts. The face on Mars is a famous example, a trick of light and resolution later revealed by better data. These embarrassments taught the community to under-enhance rather than over-enhance, to present less exciting but more reliable data. This protects credibility, but can suppress genuine anomalies if they are subtle. Wavelength differences add the final layer. NASA's instruments often look in infrared or ultraviolet, seeing heat and composition. Amateurs look in visible light, seeing shape and structure. If Atlas looks different in different wavelengths, both views can be correct. The blue halo from ionized gas might be faint in infrared. The toroidal structure shaped by magnetic fields might not appear in thermal emissions dominated by dust. This could reconcile everything. Professionals see one thing, amateurs see another, and both are true. Yet, the final, most unsettling possibility is that the discrepancy isn't about human choices at all. Maybe 3i Atlas looks different depending on how you observe it, because the object itself responds to observation. Not consciously, but functionally. If it has electromagnetic systems, active sensors like radar or radio pulses might cause it to alter its configuration, presenting a different appearance to passive optical observers versus active probes. This edges into paranoia, but it is physically plausible for a sufficiently advanced system. Stealth technology on Earth works by absorbing or deflecting probing signals. An interstellar craft might do similarly, presenting a benign, cometary face to passive watchers, while active sensors see something else. It's wild speculation, but it fits the pattern. Official images show blur, amateur images show geometry. The disconnect grows. Either NASA is hiding detail, or Atlas is hiding itself, and the data doesn't let us dismiss either possibility. Brightness pulses change everything. Several amateur observers reported periodic brightness variations in 3i Atlas from November 20th through the 30th. The variations weren't the smooth, sinusoidal waves of a rotating, irregular body. They were spikes, rapid increases followed by plateaus and gradual declines, repeating with periods between 6 and 18 hours. Extracting clean periodic signals from noisy photometric data is notoriously difficult. Atmospheric turbulence, clouds, instrument drift, all can mimic periodicity. But when multiple observers in different locations report similar periods, the signal gains credibility. If the spikes are real, they demand an explanation, and the simplest one, rotational modulation, doesn't fit. The spikes are too sharp, too episodic. Rotational light curves are smooth, predictable, tied to the object's shape. Atlas's spikes look like flashes. The beacon theory proposes these spikes serve a function. Imagine a lighthouse. Its beam sweeps across the ocean. To a distant ship, it appears as a periodic flash. If 3i Atlas is emitting directed beams of light or plasma, and if it is rotating to sweep those beams through space, observers on Earth would see periodic flashes when the beam aligns with our line of sight. This explains the sharp rise, the beam hitting us, and the gradual fade, the beam sweeping away. The periodicity reflects the rotation rate. It's speculative, but it fits the photometric data better than a passive model. Pulsars, rotating neutron stars emitting beams of radio waves, are natural beacons. Their pulses are staggeringly precise. If Atlas is doing something analogous, emitting directed electromagnetic or plasma beams, it blurs the line between natural phenomenon and engineered timing device. Oumuamua's own strange light curve was attributed to a tumbling elongated shape, but some researchers noted its brightness varied more than expected, suggesting a highly unusual, possibly flattened form. Its non-gravitational acceleration, akin to a gentle thruster burn, added to the intrigue. Atlas's brightness spikes echo this mystery. If they result from directed emissions, from plasma jets or something similar, they indicate control, direction, function. Course correction is one plausible function. Spacecraft fire thrusters periodically to adjust trajectory. If an interstellar craft were navigating a course through our solar system, it might make such corrections. The exhaust plumes, if facing Earth during a burn, would appear as a brightness spike. The periodicity could reflect a scheduled navigation update cycle. Environmental mapping is another. A craft might emit pulses to actively probe its surroundings, using the reflections to map magnetic fields, dust density or radiation. Active sonar and radar work this way. To a distant observer, these probing pulses would appear as periodic brightness variations. The symmetry of Atlas's coma could be functional too. If the glow is a protective bubble, maintaining symmetry ensures uniform protection. Asymmetric shields have weak points. Engineering favours symmetry for robustness and efficiency. The fact that Atlas maintains symmetry suggests active regulation. Systems that monitor and adjust the shield to compensate for perturbations. This is spacecraft engineering, not geology. Ancient myths sometimes speak of cosmic lighthouses, celestial beacons guiding travellers. Dismissed as metaphor, but if interstellar travel is possible, such navigational infrastructure would be logical. Beacons at strategic points, pulsing with identifiable patterns used as waypoints across the galaxy. If 3i Atlas is such a beacon, automated or carrying a signal, its periodic brightness might be its announcement. I am here. The theory remains speculative, built on patterns that might be noise, but it explains the periodicity, the sharpness, the symmetry, the brightness spikes independent of solar heating. It explains why Atlas behaves like a system, and it opens a possibility both exhilarating and terrifying, that 3i Atlas isn't just visiting, it's navigating. It's using our sun as a reference point, pulsing its presence to whatever might be listening, executing functions that have nothing to do with us, but that we are privileged or cursed to witness. If it is a beacon, the question becomes, for whom, and what happens when they arrive? The sun is not a placid sphere. It is a dynamic, magnetically fraught star. The heliospheric current sheet, a vast wavy surface where the sun's magnetic field flips polarity, extends billions of kilometers into space, warping like a twirling skirt as the sun rotates. In mid-November 2025, solar physicists analyzing magnetograph data noticed something unusual: localized warping in the current sheet. Regions where the surface dimpled inward, creating pockets of enhanced magnetic field strength. They called it dimpling. While not unprecedented, the timing and location were suspicious. Magnetic anomalies affect how solar wind interacts with objects. Comet tails are shaped by these fields. When fields are disturbed by reconnection or compression, tails can bend, brighten, or even disconnect. The November dimpling event occurred in a region of space 3i Atlas was approaching. Observers noted that the toroidal collapse of Atlas's tail coincided temporally with the peak of the dimpling. Correlation isn't causation, but the timing was noteworthy. If Atlas's strange coma resulted from interaction with local magnetic fields, and those fields were unusually strong due to dimpling, then the correlation makes physical sense. The comet entered an anomalous patch of space, and its plasma responded. Solar magnetic knots, regions where field lines tangle into complex configurations, can form during periods of activity. Within them, field strengths can be orders of magnitude higher. If Atlas passed through or near such a knot, its ionized coma would experience extraordinary confinement forces, potentially shaping it into the observed toroidal structure. This is a natural explanation, invoking only solar physics, but it requires Atlas to have encountered this rare knot precisely when we were watching, a coincidence that itself raises questions. History shows solar influence on comets. In 1910, Halley's Comet experienced a tail disconnection event driven by magnetic reconnection. In 2007, Comet Encke's tail disconnected multiple times. These events produce chaos, tails shredding, dispersing. They do not produce organized, stable tori. Atlas's tail didn't shred. It organized. It became more stable after the dimpling event. That's the opposite of the typical effect. Theoretically, charged particles encountering a region of rapidly changing magnetic field can become trapped, circulating in toroidal paths. Earth's radiation belts are an example. If the November dimpling created localized magnetic traps and Atlas's ions were captured, they could form a torus. This explains the morphology with known physics. The catch is that such traps are usually transient, lasting hours or days. Atlas's torus persisted longer, suggesting either exceptional stability in the magnetic environment or active maintenance by the object itself. If the dimpling was associated with a minor solar storm, it could have provided the enhanced magnetic environment needed to confine Atlas's plasma. Storm-associated shocks could also trigger brightness spikes, all natural, all explainable. But the precise alignment of dimpling, Atlas's passage, and our focused observation strains probability. This event connects Atlas to broader solar dynamics. It places the comet in context, not as an isolated freak, but as an object interacting with a complex variable environment. If its strangeness is just a product of rare environmental factors, then other comets passing through similar regions should show similar features. That's testable. Researchers can scour archives for comets that pass through magnetically disturbed regions. If they find similar toroidal comas, Atlas becomes less unique. If they don't, the mystery deepens because it suggests Atlas responds to magnetic fields differently, hinting at an intrinsic difference in its composition or nature. The November solar activity reframed the scientific approach. Multiple groups began modelling comet plasma interactions with higher fidelity, using Atlas as a case study. The community, initially skeptical, began taking the observation seriously, not because they believed in artificiality, but because the data demanded better physical explanation. Natural or not, Atlas was teaching us about extreme plasma dynamics in space. The dimpling event was a wake-up call, a reminder that space is weirder, more textured, and more magnetically complex than our models often assume, and 3i Atlas, whether by chance or design, sailed right into the heart of that complexity. Radar imaging is a powerhouse of planetary science. By bouncing radio waves off asteroids and comets and analysing the echoes, we can determine shape, rotation, surface roughness, and composition. It sees through darkness and clouds. It provides spatial resolution that optical telescopes cannot match for nearby objects. But radar's range is limited. Signal strength falls off with the fourth power of distance. Imaging objects in the outer solar system requires immense power and sensitivity. In October 2025, funding proposals from NASA, ESA, and JAXA for deep space radar upgrades suddenly accelerated through bureaucratic channels at breakneck speed. Each agency independently requested budget increases, citing planetary defense and scientific interest in interstellar objects. The timing raised eyebrows. Budget cycles are slow. Major infrastructure projects take years of planning. Yet, within weeks, funding was allocated, contracts issued, timelines fast-tracked. Officially, the push responded to the growing awareness that interstellar objects are more common than we thought. Unofficially, whispers pointed to 3i Atlas as the catalyst. The upgrades focus on increasing transmitter power and receiver sensitivity. Current facilities like the Goldstone Deep Space Network can image objects out to tens of millions of kilometers. The goal is to double or triple that range, reaching into the asteroid belt and beyond. The technical challenges are monumental, the costs in the hundreds of millions. Such expenditure demands justification. Speculation centers on classified observations. Some theorize that early faint radar echoes from Atlas suggested structural details, flat surfaces, sharp edges, reflectivity anomalies that sparked urgent concern. Radar can distinguish a solid, possibly metallic object from a porous rubble pile. If Atlas returned a signature inconsistent with a natural comet nucleus, it would justify an all-out effort to get a better look. The problem is timing. By the time new facilities come online in 2026 or 2027, Atlas will have passed perihelion and be receding. The window for high-resolution radar imaging is narrow, perhaps already closed. That urgency aligns with a scenario where authorities want to characterize this object before it's gone forever. Planetary defense provides convenient cover. Governments have become more serious about asteroid threats. Funding radar upgrades fits that narrative. but the language in proposals specifically emphasized interstellar objects. Interstellar objects pose no collision risk on human timescales. They pass through once. Spending vast sums to image them makes scientific sense, but not primary defense sense, unless the objects are considered a different kind of threat. Radar is the ultimate test for artificiality. A natural nucleus is irregular, lumpy. An engineered object likely has geometric features detectable in high-resolution radar. If Atlas were imaged and showed such features, the debate would end, we would know. The absence of public radar images fuels speculation. Either attempts failed due to range, or they succeeded and the results are classified. Either scenario is unsettling. The push also makes sense as scientific infrastructure. We've now detected 3 interstellar visitors accidentally. A dedicated early warning system for such objects is prudent. Radar would be key for rapid characterization. Building that capability now, while public and scientific attention is focused on Atlas, is strategically smart. Subtle indicators point to institutional mobilization. Prominent radio astronomers quietly shifted focus to solar system radar. Job postings appeared for radar signal processing specialists with security clearances. Dormant international collaborations reactivated. These are not smoking guns, but they paint a picture of a community responding to a perceived imperative. Are institutions seeing something we aren't? Almost certainly. Space agencies have access to data streams not publicly released, observations from classified satellites, radar from military facilities, spectroscopy from instruments whose existence is not public. If any of those sources revealed anomalies in Atlas, the information would be tightly controlled. The public would see only the conservative, natural interpretations. Behind closed doors, very different conversations could be occurring. This isn't necessarily conspiracy. It's how national security functions when confronted with an unknown of potential significance. If Atlas represents a fundamental challenge to our understanding, then silence, controlled messaging, and sudden urgency all make sense. They're not necessarily hiding aliens. They could be managing uncertainty, avoiding premature disclosure that could cause societal harm without benefit. We, on the outside, can only infer from the patterns. Something about 3i Atlas changed the game. Artificial intelligence has quietly revolutionized astronomy. Machine learning algorithms trained on millions of labeled images now classify galaxies, find exoplanets, and detect supernovae faster than humans ever could. In 2025, autonomous astrophysics models, AI systems designed to sift through petabytes of archival survey data without human supervision, began flagging anomalies. These systems learned normal from decades of observations, and in learning normal, they became exquisitely sensitive to the abnormal. Trajectory outliers appeared immediately. The AI identified hundreds of objects whose orbits didn't fit standard categories. Most were data errors. But a small, persistent subset were real objects with unusual motion. Some were long-period comets with strange orbits. Others were hyperbolic, potential interstellar visitors that predated Oumuamua but had gone unnoticed. The AI flagged them not because it was told to look for interstellar objects, but because their trajectories were statistical outliers in the high-dimensional space of orbital elements. Machine learning's strength is pattern recognition in complex data. Humans reason well but struggle with high-dimensional spaces. AI excels there. When trained on orbital data, light curves and spectra simultaneously, it can identify clusters of similar objects, even if those clusters don't match human categories. In the 2025 analysis, one cluster stood out: objects with hyperbolic orbits, low perihelia, and anomalous brightness behavior. The cluster included 3i Atlas. It also included several previously uncatalogued objects from archival data. This suggested Atlas might not be unique, but part of a population we've been missing. The AI classified Atlas as non-standard, not a comet, not an asteroid, but something its training data lacked examples to categorize. This is profound and frustrating. The system recognized Atlas as different but couldn't say why in human terms. Its internal representation placed Atlas far from known comets in feature space, close to nothing else. Researchers found this region was characterized by high symmetry scores, tight coma confinement, and brightness variability uncorrelated with solar distance. Exactly the features human observers had noted. The AI discovered them independently, without bias. Human taxonomy for solar system objects has fuzzy boundaries, but it works. AI taxonomy discovers categories from data. When an object falls outside all discovered clusters, it suggests the object genuinely doesn't fit. It is something else. There's a risk of misclassification. If the training data lacks diversity, e.g. use few interstellar examples, the AI might label rare natural phenomena as anomalous simply because they're rare. But the AI also flagged Atlas for features unrelated to its interstellar origin. The symmetry, the brightness spikes. These aren't intrinsic to being interstellar, they're intrinsic to Atlas itself. The AI recognized that Atlas behaves differently from all comets in its training set, including models of what interstellar comets should look like. AI can also generate hypotheses. Generative models, trained on physics simulations and data, can suggest what combinations of parameters, composition, rotation, magnetic field, might reproduce observed features. Early results indicated that reproducing Atlas's symmetry and torus required either extreme rotation with high tensile strength or moderate rotation with magnetic confinement. Both are edge cases, possible but highly improbable. The AI, in essence, confirmed human intuition. Atlas is weird, and explaining it requires invoking rare conditions. If the AI identified similar objects in archival data, it implies a population of interstellar visitors, some of which might have been misclassified or missed. Most would be natural, a few might be rare configurations, and a vanishingly small number might be something else entirely, engineered probes drifting through the galaxy. The statistical analysis is preliminary, but the hint of a population raises the stakes. If Atlas is one of many, studying it becomes even more urgent. Public awareness of these AI discoveries is minimal. They appear in specialized journals, but the infrastructure for rapid AI-driven anomaly detection is now in place. When next-generation sky surveys like the Vera Rubin Observatory come online, generating terabytes of data nightly, AI will be the first line of analysis. Humans will follow up on AI-flagged targets. The pace of discovery will accelerate. If another Atlas-like object appears, amateurs and AI will flag it simultaneously, and the conversation will be public from the start. The convergence of science, AI, and 3i Atlas points to an uncomfortable conclusion. The tools we built to explore the universe are now revealing that the universe is stranger than our frameworks can easily accommodate. Atlas challenges our taxonomy, our physics, our assumptions. An AI, blind to our biases, confirms it. The object doesn't fit. It is alone, or part of a tiny, unrecognized population. And whether that population is natural or artificial, its existence demands we expand our understanding of what moves in the dark between the stars. Fusion propulsion has been a dream for decades. The energy density of fusion, the process powering stars, dwarfs chemical rockets. A fusion-powered spacecraft could reach a significant fraction of light speed, making interstellar travel conceivable. The perennial challenge is confinement, containing million-degree plasma. Magnetic confinement in toroidal fields, as in tokamaks, is the leading solution on Earth. In November 2025, a research consortium unveiled a new fusion probe concept, a spacecraft design using toroidal plasma loops not just for power, but for propulsion. The design is elegant. Instead of a traditional nozzle, it uses magnetic nozzles to shape fusion plasma exhaust into a directed jet. The magnetic fields confine the plasma in a toroidal loop around the craft's midsection, heating it to fusion temperatures. The energy heats the plasma further, and magnetic gradients direct the flow rearward for thrust. From a distance, such a craft would appear as a glowing toroidal ring surrounding a central core. The plasma would emit light from fusion reactions and recombination. The resemblance to 3i Atlas's blue halo is unsettling. Same shape, same glow, same tight confinement around a central nucleus. Toroidal fields stabilize plasma by eliminating endpoints where it can leak. This topology minimizes energy loss, allowing sustained confinement. It's why tokamaks are donut-shaped. It's why the fusion probe concept uses a torus. And it's why, if an interstellar spacecraft used plasma for propulsion or shielding, a toroidal configuration would be the natural physics-favored choice. Nature sometimes mirrors engineering because both obey the same physics. The shapes that minimize energy, maximize stability, recur. The fusion probe concept solves two critical problems: energy and time. Fusion provides the energy density for high-speed travel. Magnetic confinement allows control over centuries-long voyages. Such a system could theoretically operate for millennia. If an advanced civilization developed interstellar travel, this, or something like it, might be their solution. And probes they launched would glow with toroidal halos visible across light years. The comparison with Atlas is speculative but grounded. Atlas has a toroidal halo. The Fusion probe predicts a toroidal halo. Atlas brightens independently of the sun. Fusion reactions generate light independently. Atlas shows tight plasma confinement. Fusion requires tight plasma confinement. The parallels don't prove Atlas is a fusion craft, but they demonstrate that if it were, it would look much as it does. This is the uncomfortable overlap where observation meets speculative engineering. NASA's own research into plasma propulsion includes projects like the Vassimar engine, which uses radio waves to heat plasma and magnetic nozzles to direct it. Scaling such concepts to fusion levels is a huge leap, but the physics is the same. If we can conceive it, a more advanced civilization could have realized it. Magnetic nozzles, plasma mirrors, magnetic shielding, all are active areas of human engineering research. If Atlas uses similar techniques, it's doing nothing we haven't imagined. It's just doing it better, at a larger scale, and it's already here. The convergence is what chills. This month, engineers unveil a fusion probe concept that looks like Atlas. This year, Atlas exhibits behaviors consistent with that concept. The resemblance is specific, structural. Physics favors certain solutions. Toroidal magnetic confinement is one. If both nature and engineering converge on the same solution, distinguishing between them becomes nearly impossible without close inspection. Atlas might be a natural comet in a rare state that mimics fusion signatures. Or it might be the real thing, a probe, ancient and silent, still executing its million-year-old mission. The data doesn't let us choose, and that ambiguity, the inability to definitively say what we're looking at, is perhaps the most unsettling aspect of the entire mystery. We see something that looks engineered, behaves like a system, and matches our own speculative designs for interstellar travel, and we cannot prove it's anything more than the universe's most elaborate cosmic coincidence. Space is not empty. Even in the vast reaches beyond Pluto, microscopic dust particles drift, remnants of comet trails, asteroid collisions, and interstellar influx. These particles are tiny, but at high speeds, they are hazardous. For an object travelling between stars, dust is an existential threat over millennia. In late 2025, data from the New Horizons spacecraft, now far beyond Pluto, revealed a previously undetected structure, a massive diffuse dust arc in the outer solar system. It was dark, low reflectivity, and had gone unnoticed until analysts looked at faint scattered sunlight at extreme angles. Its origin is unclear, primordial material, or debris from a recent Kuiper belt collision. But its presence means the outer solar system is dustier than models predicted. For an interstellar object like 3I Atlas, entering this dustier environment changes the survival calculus. After millions of years in the sparse interstellar medium, it would suddenly face a much higher impact rate. Without enhanced protection, its surface would be sandblasted, eroding rapidly. The fact that Atlas appears intact, with a tightly confined symmetric coma, suggests it is managing the dust environment effectively. Plasma bubbles can act as shields. If a bubble is dense enough to ionize incoming dust particles charging them, then magnetic fields can deflect them. This requires continuous energy. A passive comet cannot do this. An active system could. The fusion probe concept inherently includes magnetic shielding. The same fields that confine plasma for propulsion also deflect particles. If Atlas is such a craft, its toroidal halo isn't just for show, it's armor. For natural comets, passing through dustier regions should trigger outbursts. Impacts heat the surface, vaporizing ice, expanding the coma. This would look like chaotic brightening. Atlas's brightness spikes are controlled, periodic, not chaotic. They suggest active management, not passive response to impacts. The dust arc discovery ties the narrative together. Solar magnetic dimpling creates unusual plasma environments. Radar upgrades aim to see into those environments. AI detects anomalous objects. Fusion probe concepts predict toroidal plasma shields. and now a dust arc explains why such shields would be necessary for long-term survival in galactic travel. Each piece is independently plausible. Together, they form a coherent, if speculative, picture. Atlas enters a solar system more complex than we knew, navigates magnetic anomalies we just detected, exhibits shielding consistent with concepts we just engineered, and behaves in ways our best AI flags as non-standard. None of this proves artificiality. All of it suggests something extraordinary is happening. If 3I Atlas is just a comet, it is the strangest comet ever recorded, exhibiting every trait that would make us suspect artificiality without crossing into proof. It maintains symmetry that demands active regulation. It confines its coma in ways natural physics struggles to explain. It spikes in brightness independently. It survives environments that should shred it. And it looks, from certain angles, exactly like a fusion-powered spacecraft with magnetic shielding. The alternative, that Atlas is an engineered object, a probe or derelict, fits the data at least as well. But accepting that means accepting we are not alone, that other intelligence has left artifacts adrift in the galaxy, artifacts that occasionally pass through our neighbourhood. That is a threshold most hesitate to cross without overwhelming evidence. The story of 3I Atlas is still unfolding. Data accumulates, AI refines, engineers iterate. The mystery deepens, not from lack of information, but because the information points in directions we are unprepared to follow. Sometimes anomalies are noise, sometimes they are signals of new physics, and sometimes, rarely, they are messages, intentional or not, from intelligences we've never met, artifacts of civilizations beyond our imagining, drifting through the void, waiting for someone curious enough to notice. 3 Atlas might be rock and ice, shaped by chance into a perfect mimic of design. Or it might be exactly what it looks like. A traveller, ancient and purposeful, executing a mission we can only guess, crossing our path for a brief moment before vanishing back into the dark. The data doesn't let us decide, and maybe that's the point. Maybe the universe offers mysteries not to be solved, but to remind us how much we don't know, how vast the cosmos is, and how much remains, waiting in the silence between the stars.